Number 10. Well, number 10 has a lot of information, and this is a really good place to point out what is extra information and what you actually need. So you actually need that you have a 100 milliliter solution. What you don't need is all of the stuff inside of it, at least not yet. So it was adjusted to a pH of 5.5 with an acetate buffer, and it was treated with more EDTA than it needed. And more EDTA than it needed was 10 milliliters of 0.0400 molar EDTA. And that was to bind all of the metal ions. So then for the excess EDTA, we needed this amount of zinc sulfate for the back titration. So we measured all of the ions in the unknown. So first, let's find out how much EDTA was used to measure all of those ions. That's a really good place to start. So the total EDTA is going to be equal to the moles of EDTA used for the solution for all the metals plus the moles of EDTA in the back titration. So the total EDTA added, we have 0.01000 liters of a 0.0400 moles per liter EDTA solution. I flipped that upside down. So it's 0.04 this way, moles on top. That makes so much more sense. And 1 liter. So then we get 4.00 times 10 to the negative 4. That is moles of EDTA. And that is our total. So that's going to go right here. Well, let's use scientific notation. I think we need, three significant figures for that. So now we can calculate how many moles of EDTA was used in the back titration. So this was the excess here. So we have 0.00505, and that's liters of the zinc sulfate solution. And we're going to multiply that by the molarity, 0.0262, and that's moles of zinc sulfate solution per liter. Zinc sulfate solution. And in the zinc sulfate solution, we have 1 mole of zinc. And 1 mole of zinc reacts with 1 mole of EDTA. So what we're left with when we perform this calculation is then the moles of EDTA that were in excess. And I get 1.31 times 10 to the negative 4. And that's moles of EDTA. That is the excess. So how many moles of EDTA were used to complex all of those metals? Well, it's a simple subtraction problem. And I get the moles of EDTA that were used for all of the metals are equal to 2.69 times 10 to the negative 4. And again, that is moles of EDTA. Now we can move on to the next part of the problem. To measure mercury 2, the solution at the end point of the titration was treated with 100 milligrams of Ki to form Hgi4 and liberate the EDTA from the Hg2+, but not from any other metal. So liberated EDTA required 5.81 times 10, 5.81 milliliters of 0.0262 molar zinc sulfate. So we find out how many moles of zinc sulfate that is, 0.0262, and I get 1.52 times 10 to the negative 4. So that is the number of moles of EDTA released by the mercury 2. So in question A, from the first titration, find the total millimoles of metal ions in the unknown. Well, that's going to be equal to this value, the 2.69 times 10 to the negative 4. In B, from the second titration, find the millimoles of mercury in the unknown. Well, that's going to be equal to this value. Now, I calculated moles. They would like millimoles. The difference between moles and millimoles is a factor of 1,000. So for A, the total millimoles of metals in the unknown, that would be 0.26. Let's see, I have 9. The answer in the book, it looks like 268, but I have 269. Regardless, close enough. And from the second titration, millimoles, let's use the right abbreviation, 0.152 millimoles. Number 11, we have a sulfide ion determined by indirect titration. Solution containing 25 milliliters of this copper substance plus 15 milliliters of a 1 molar buffer, pH 4.5, added to 25 milliliters of an unknown sulfide solution. The precipitate was filtered and washed, ammonia added to the filtrate until the blue color was observed. Titration of the filtrate with this concentration and volume of EDTA to reach the endpoint. Find the molarity of sulfide in the unknown. Well, we need to start with what is the precipitation reaction. So we need copper ion plus sulfide reacts to form CuS solid. So the total copper used is going to be equal to this many moles. So we would calculate that first. So I get 1.0830 times 10 to the negative third moles of copper, because that's the copper that was added. Now the excess copper is then going to be, we find the excess copper by finding out how much EDTA is required, 0.01211 liters times 0.03927 moles per liter. So this gives us 4.756 times 10 to the negative 4 moles, or 0.4756 millimoles. And that is the moles of EDTA, which is also going to represent the moles of excess Cu2+. Now, if we have the total moles of copper and we subtract out the excess moles of copper, what's left are the moles of copper used for the precipitate. So we should get, let's see, I get 6.074 times 10 to the negative 4 moles of copper that were used for the precipitate. So then let's go back. Titration required, reaching out, find the molarity of the sulfide. Well, now we need this equation here. It's a 1-to-1 equation. So moles of copper 2 are going to be equal to the moles of the sulfide. But we need the molarity. And because we need the molarity, we need the total volume. Nope, in the unknown. So we need the volume of the unknown. So 0.025 liters. And I get a molarity of 0.02430, capital M, molar. Number 12, we're going to calculate and we're going to propagate some uncertainty. So the potassium ion in a 250 milliliter water sample precipitated with sodium tetraphenyl borate. Precipitate, filtered, washed, dissolved. And then we have this reaction here, the organic treatment with an excess of mercury 2 EDTA. Liberated EDTA titrated with this amount of zinc. Find the concentration and uncertainty of potassium. Well, we're going to start with our volume of zinc because we're going to find out how much zinc was required to titrate that liberated EDTA. So we're going to start here, 0.0437 moles, and this is zinc 2 per 1 liter. Now our zinc can be equated to moles of EDTA. So 1 mole of zinc is 1 mole of EDTA. Now we need to look at the stoichiometry in our equation here. We have 4 moles of liberated EDTA and 1 mole of our sodium tetraphenyl borate. And then the stoichiometry here, this is 1 to 1. So if we cross this way, we can say 1 mole of potassium will produce 4 moles EDTA. So now we can calculate how many moles of potassium were in the original sample. And I get 3.13, I gave it away, 87, and it keeps going, times 10 to the negative 4, and this is just moles of potassium. The question was, what is the concentration? So the concentration of this, we then need to divide this by the volume, the 250 milliliters. So this in my calculator, 3.1387, and it continues. It's just going to stay in my calculator. Moles divided by 0.250 liters. You should get a molarity then of 1.25, and then I get a 5 there. So I'm going to round that to a 6, 1.26. Yeah, I do have 3 sig figs, times 10 to the negative 3rd, and that is a capital M molar. So now we need to propagate that error. We were doing a lot of multiplying and dividing here. So we need to be using our percent E equation. So we need those relative percent errors. So I'm going to write it all out because I just want to be as clear as possible. The error for this value was 0.03 milliliters. So to get the relative percent error, it's 100 times 0.03 divided by 28.73, and then we're going to square that business. Then for the next one, for the molarity of zinc here, 100 times, let's see, I believe that's 3 zeros and a 1 divided by 0.0437 squared. These are absolute numbers. They don't have uncertainty. These are absolute numbers. They don't have uncertainty. Then we have this value, this volume value, 100 times 0.1 divided by 250, and square that. So I get an error then, an error percent of 0.255%. So you could say that this would be 1.26 times 10 to the negative 3rd, capital M molar, and then in parentheses plus or minus 0.255%. Or you can convert that to standard error, where we would take that percentage that's currently in my calculator. Remember, the percent is going to be equal to 100 times the error divided by the value. So in this case, the percent is known, 0.255. The value is known, and that's 1.26 times 10 to the negative 3. And what we need to solve for is the error. And what I get then is that that error is equal to 3.213 times 10 to the negative 6. We round this to one significant digit. This would be 1, 2, 3, 4, 5, 3, like this. So we could say 1.26 times 10 to the negative 3 plus or minus 0.12345 3 molar.